Okay, kind of closing out chapter 5 here. There's really one more style of problem that we want to discuss, and this type of problem would relate well to laboratory experiments as well. So if you're in a hybrid class where you're still getting laboratory experiments, this is an experiment we will generally do at some point in the lab. And this basically combines the two sections or two parts of this chapter. We're going to combine the part where we use temperature change to figure out how much heat is transferred, right, along with something like specific heat capacity. And then we're going to apply that amount of heat to determining the enthalpy of a particular reaction. So we're going to kind of piece those two pieces of information together. And experimentally, this is called calorimetry. So calor also means heat, similar to thermo. So this is basically measuring heat. So we're measuring how much heat is produced or absorbed when a reaction happens, and we're using that to figure out its enthalpy. So let's look at the problem, and then let's see if we can apply what we've already learned to work our way through it. Okay, we've got 200 milliliters of 0.4 molar HCl. So notice those are both three significant figures. We've got the decimal there after 200. And we're mixing that with 200 milliliters of 0.4 molar sodium hydroxide in a coffee cup calorimeter. So a calorimeter is just where we're measuring heat. Like a styrofoam cup is not a bad place to do that because it insulates pretty well. Not much heat is lost to the cup or to the surroundings when you do that. The temperature of the solutions before mixing was 25.10 degrees C. After mixing and allowing the reaction to occur, the temperature is 27.78 degrees C. So the temperature went up, right? So there's a temperature change in there that we can use. We want to calculate what is the enthalpy change when 1 mole of acid is neutralized, right? And we're given some extra information. Assumed densities are 1 gram per milliliter, and specific heats are 4.20 joules per gram degree C. So that's just rounded a little bit from the 4.184 that we've been using for water. Okay, so we want to get to enthalpy. Enthalpy, of course, is related to how much heat is produced. So the first thing we should figure out is the quantity of heat. So how much heat is produced here in this reaction? Now we should, by this point, be fairly familiar with our formula. The quantity of heat produced is equal to the specific heat capacity of the material times the mass of the material times how much the temperature changed. And we've got enough information to figure all of that out. Okay, so we're told we can use a specific heat capacity for this solution of 4.20 joules per gram degree C, right? And these are aqueous solutions, so they're mostly water, so it shouldn't be too surprising that it's right around what water is here. In fact, that's not a bad assumption to just use water here for an aqueous solution. The mass here, we started with 200 milliliters of one solution and combined it with 200 milliliters of another solution, so that's 400 milliliters total. We're told to just assume that the density is 1. Again, that's reasonable for water. So if we have 400 milliliters, that would be 400 grams. Three significant figures there. Right? And then the temperature change, right? Both solutions started at 25.1 and the temperature went up to 27.78. So that is, so we can write that out just to be sure, but I think I can do that one in my head. Final temperature minus initial temperature here. 8 minus 0 is 8. 7 minus 1 is 6. 2.68 degrees C is our temperature change. And it did go up, so depending on whether you like to use the negatives or not, it shouldn't be negative here, it should be positive, right? But again, you don't need the negatives, you can think about direction instead of using the negative sign if you don't like the negatives. Okay, multiply that out, grams is going to cancel, degrees C is going to cancel. This will give us how much heat was produced by this reaction. So 4.2 times 400 times 2.68, 4,502.4 joules. Now, it's 3 sig figs at this point, but I'm going to keep all that information because I am not done with the problem just yet. That's how much heat was produced by this reaction. Now, we want to take this heat and we want to turn it into an enthalpy. So there's really two considerations we need to factor in when we're doing that. Heat is just measured in joules, but remember enthalpy is measured in joules, well, generally kilojoules, but per mole. So if we're going to transition this to enthalpy, we need to divide by how many moles of one of the components reacted in our reaction. And we should also change this to kilojoules. So maybe there's three things. I was leaving out the kilojoule change. The other thing we need to consider is sign, because heat is related to kinetic energy, whereas enthalpy is related to potential energy. They're going to have different signs. If there's a positive quantity of heat being produced, that means the enthalpy should be negative. And vice versa. If the temperature went down and we actually lost heat from our surroundings, that would mean that heat went into the reaction. That negative change in heat would correspond to a positive change in enthalpy. So let's apply all three of those steps. We can change this to kilojoules just by moving the decimal 3 places. Right? So let me write in unit-wise how we would do that, but it will just move the decimal 3 places. There is 1 kilojoule for every 1,000 joules, so just dividing by 1,000, that would be 4.5024 kilojoules. Now, we want to change that to negative, and then we want to divide by the quantity of moles, so moles on the bottom. Now, we can figure that out from the volume that was provided up here. So we were actually asked to calculate enthalpy change in terms of a mole of acid. Since this is a one-to-one reaction, it could be a mole of base as well, although that would be worth looking at too. We've talked about these reactions. This is an acid and a base, NaCl. HCl is hydrochloric acid, NaOH is a base. Acids and bases combine to give water and a salt. The salt in this case would be sodium chloride. So this is a one-to-one reaction. It's already balanced just like that. So 1 mole of HCl would react with 1 mole of NaOH. But if we want to know how many moles of HCl we have, we could start with 200 milliliters of the HCl solution. The molarity was given, it's 0.4, so that would be 0.400 moles of HCl per liter. I'm going to change that liter directly to 1,000 milliliters. And that would be how many moles of HCl reacted here. And again, we need that because enthalpy is on a per mole basis. So the enthalpy is not just how much heat, it's how much heat relative to how many moles reacted. So it would be 0.08 moles of HCl. So if we take the heat that was produced in kilojoules and then divide by how many moles reacted, that will give us the enthalpy in terms of hydrochloric acid. So 4.5024 divided by 0.08. And then 3 significant figures for our answer would be negative 56.3 kilojoules. And that would be the enthalpy change for this reaction. Okay, so hopefully you get a chance to try that out in lab, doing that sort of calculation. But if you're just doing the calculations as you're practicing, or if if it's a completely online class, you might just get a set of data where you're supposed to do these calculations. Keep those 3 things in mind. Heat is generally going to be in joules because it's coming from specific heat capacity. So when you turn that heat into enthalpy, you've got to change to kilojoules. You've got to divide by the quantity of moles that reacted, and you've got to flip the sign. Right? Heat is related to kinetic energy, but enthalpy is related to potential energy, so they're always going to be opposite each other in terms of sign. Okay, that wraps up chapter 5, so we'll close the video there, and stay tuned for chapter 6.